Okay, the second video for section 8.7, just Taylor and Maclaurin series. We'll start here with the binomial series, and this is coming up with a power series representation for a function 1 plus x to the power of k. So our binomial is 1 plus x, and then we're raising it to some power k, and k is any real number. So we noted that if k was some natural number, in other words, some positive whole number, then it would be a finite length polynomial. We could expand that through use of the binomial theorem to write down what all the coefficients were with the powers of x and 1 that are involved. But if k was just a real number, that could be a decimal number or fraction or even some irrational number as well. So we'll see how to handle that. And it'll turn out that when k is just a real number and not particularly a natural number, then this will be an infinitely long power series. Um, so to come up with one for k, some real number, so a Maclaurin series for this function, 1 plus x to the k, we'll start with the usual method. Write down the first few derivatives of f. Function initially is 1 plus x to the k, its first derivative. Power rule gives us factor of k with a new exponent of k minus 1. Each subsequent derivative steps down 1 in the power, and we add a multiple of k or k minus 1 and so on downward as we go through the derivatives. So it looks like f sub n, or the nth derivative of f at x. We can kind of see the pattern here. It's almost all the factors of k except of k factorial, but it's missing k minus n factorials. In other words, this one is cut off at k minus 3 and lower. So k minus 3 factorial is cut out of our k factorial. Same thing here, k minus 2 and lower, or in other words, k minus 2 factorial is chopped out of k factorial in this case. So that's exactly what this says. K factorial divided by k minus n factorial comes out to, well, k times k minus 1 times k minus 2 all the way down to k minus n plus 1. So that is actually written a little further away from us in the page down here. Exactly what I said is written there. And that's actually the more useful thing to keep in mind. The book does have this factorial notation that we have here. And we'll talk about what that means in terms of a natural number and what we can do. Of course, we're thinking about things in terms of a natural number here. But anyway, we've got our coefficients, our constants taken care of here. We've got the 1 plus x portion to take care of, and we just note that at each derivative, k minus whatever this number is matches each of the derivative counts. So that's just k minus n for all of those, for all cases. So 1 plus x to the k minus n power. So now we've got our general term for f sub n of x. It's a Maclaurin series, so we're going to let x be equal to 0 and evaluate the nth derivative of f at 0, as we see here, to come up with part of our coefficient c sub n. So when x is equal to 0, we have 1 plus 0 as our binomial. That's just 1. 1 to any power is just 1. So this simplifies to just this term, the k factorial over k minus n factorial. So now when we put that expression over n factorial, we arrive at this full expression right here. So in other words, this with a factor of 1 over n factorial gives us this one. So that's our general nth coefficient. And again, the more useful way to write this, and it's expressed below in this way, is in this form, and we'll see why in a moment. For natural numbers, this is well defined, but if for natural numbers k. But if k is a natural number, like I said, this expansion 1 plus x to the k is a finite length polynomial. It doesn't need a power series expansion. It's a finite power series. So we think about power series as being infinitely long polynomials. The next thing better than an infinitely long polynomial is a finitely long polynomial in terms of being able to manage things. So anyway, with these two different expressions, I've listed them both because in the notes I have this one on the next page, and the book uses this as well. but the book also lists this one. I don't have that on the next page, but this is the more useful formula to use for problems that we'll see moving forward from here involving the binomial series. Now, remember that this works for a natural number k because k factorial is well defined. So this is a fine expression for a natural number k, but again, that's not really an interesting power series. It's a finite polynomial when k is a natural number. On the other hand, if k is not a natural number, this is well defined still. K times k minus 1. So if k was equal to 1/3, then we could still manage this. We don't have to think about what 1/3 factorial is. Note that n is still in factorial because n is still going to range over the integers, the positive integers out towards infinity. So it still makes sense to leave n as in factorial. So that's why this expression is more useful than the one above. So we've established the binomial, the power series for the binomial, or the Maclaurin series for the binomial at least, and that's given here as well. It's even given in this case with its radius of convergence. That's an absolute value of x strictly less than 1. We haven't established that, so let's go ahead and do that. Let's prove that the radius of convergence for this power series is 1. So the way you do that is the ratio test, as always. The limit as n goes to infinity of the n plus 1 term divided by the nth term, or in other words, times 1 over the nth term, or times the flip of the nth term. So all that has been done sort of quickly here because we've had a lot of practice with these by now. And we note that k factorial canceled with k factorial. We have n factorial over n plus 1 factorial. We'll group those here. And then we've got k minus n factorial over k minus n plus 1 factorial. That's this grouping. And then we have our powers of x's as this ratio right here. So all of this needs to be less than 1 in order for this power series to converge. So that what implications does that have for our x values? Well, let's find out by simplifying this and taking the limit. Well, n factorial over n plus 1 factorial cancels to 1 over n plus 1. N plus 1 factorial contains all of n factorial plus that copy of n plus 1. Then k minus n factorial over k minus n minus 1 factorial. This one is a step down from the one above in factorials. So all of those, all the factorial terms cancel, and we're just left with k minus n. So this expression is k minus n over n plus 1. Our x terms cancel to x. All of this needs to be less than 1 after we take the limit. So let's see where we end up. This is negative n minus k over n plus 1. Well, this is an absolute value, so the minus sign really doesn't make much of a difference here. And what we see is that we have n over n as our lead terms. This limit only cares about n, so k and x are fixed in this. K's been fixed all along, keep in mind. We did not change k's index when we plugged it in here because we're looking at the limit as n goes to infinity, not k. So n over n, that's a matched degree polynomial, a rational function. So this is a limit of 1. So we see here, absolute value of x times 1. And all that needs to be strictly less than 1. And we just arrive at our radius of convergence being positive 1, or just 1. So the interval of convergence, since we're centered at 0, is from -1 to +1. And that's our interval of convergence and radius of convergence for the binomial series. Now let's find the binomial series for a given binomial function. This is where it gets a little bit more interesting. So we're asked to find a binomial series, or to find a power series for this given function. Now they just say a power series, so we could find any power series. Well, the easiest power series to find is the Maclaurin series, centered at 0. That should simplify our lives. Maybe in this case, the easiest one would be a power series centered around x equals 1, because that's probably going to 0 everything out. But that's not a very useful power series, so let's not do that. So Maclaurin series centered at x equals 0. We make a note that the fourth root of 1 minus x is really 1 minus x, a binomial, raised to a 1/4 power. So now we have a non-natural number exponent, and that's what I was hinting at before. This could be a little tricky, but we at least have something we could take the derivative of pretty easily. So let's do that. F prime, F double prime, so on until we feel like we've got the hang of the pattern here. And power rule gives us 1/4, 1 minus x to the negative 3/4. Then negative 3/4 times 1/4, 1 minus x to the negative 7/4. Just cranking along. I don't multiply these terms together right away because I want to see what kind of patterns coming out. I don't really care what the numbers are as single values, numerator over denominator. I want to see each of those fractions so I get some idea of the power. Now by the third derivative, we see that we have 4's in the denominator, and we realize, well, that's never going to change. So we're always going to have a 4 in the denominator. And that matches third derivative, 3 factors of 4 in the denominator. Second derivative, 2 factors of 4. So we've got 4 to the n in the denominator for all of these. We'll see that over here. 4 squared, 4 cubed, 4 to the 4th. So that's one part of the pattern. Now the top is a little more interesting. We keep subtracting 4 over 4, or 1, from each of these powers because we're taking the derivatives as we move down the line here. Well, that's causing us to step by values of 4 in the numerator and list these factors out. It's probably easiest just to stick with writing these down as we see them. We're going to have to be a little bit more direct, a little less tricky with this because it's not really easy to come up with a nice clean representation of this list of multiples. Now, once we've got our derivatives written and we feel like we've got a decent handle on things, we know that the next one in this pattern will be a multiple of 15. And we're also alternating signs, minus, plus, minus, plus. You see that. And we also realize that the 0th term is going to be a bit of an oddball, possibly. So we'll just leave that to itself. Anyway, here we have our evaluations of f at 0, since it's a Maclaurin series. So for all our x values, we plug in 0. In this case, this is quite nice. 1 minus 0 to the 1/4 is just 1. And we keep moving. 1 minus 0 to the negative 3/4 is 1 times 1/4. And we just get 1/4 here then. And we realize that this is a pretty easy simplification. It's just these terms that are going to survive. So we have following, and we see our powers of 4. We see an alternating plus or minus sign once we hit the second term. Notice that wasn't the case for our 0th and first term. So what we'll have to do is probably separate these two out on their own and then start our series off at this second derivative and then crank through infinitely many terms from there. The last thing to do is to come up with our general series coefficient is to divide each of these by n factorial. And here we have off to the right where that's happening. C naught is 1 over 0 factorial, which is 1. 1 over 4 times or divided by 1 factorial, and then divided by 2 factorial, by 3 factorial. So it's just introducing a small little bit, just the n factorial to each of these. And our general term, with some amount of, maybe a little bit of thinking here, and this is a general term only for n greater than or equal to 2, we need negative 1 to the n, because our even terms, nope, we actually have a small typo. We need negative 1 to the n plus 1 because our even terms need to be negative. So this needs to be a plus 1 right here. So when that's the case, our even terms will be negative and our odd terms will be positive. So that takes care of that. And we see that 4 to the n is our nth term. So that's completely acceptable based on what we see above. And n factorial came from our C sub n definition. The last thing is to note that all of these will count down or count up to 3 times 7 times 11. And then this goes all the way up to 4n minus 9 times 4n minus 5. And 4n minus 5 will be the last term for any n that's greater than or equal to 2. So I'll let the reader check that this formula, this sort of setup, works for all of our previous terms stopping at the second derivative. It shouldn't work for this one because this one's sort of an oddball as well as that one. So this captures the pattern. It's not the nicest thing to have to write down, but it'll have to do the trick. Maybe if we thought much harder, we might be able to come up with something slightly better, but these are difficult. Long strings of multiples like this can have very complicated general terms. This is a decent iterative way to get there, so we'll just stick with it. So since that's our general term, and we know that these two are oddballs, well, we know that C naught is times x to the 0th power. So this is just a 1 times 1. This is C1. C1 is actually 1/4, well, it's just 1/4, times x to the 1st power. So it's 1/4 x. And then the rest of these terms fall into the series. So we have 1 plus 1/4 x for our two oddball terms. And then we've got our series, as we suggested before, from our general term C sub n. Each of those, all those terms are times this x to the n power, and we've closed this one up. These tend to be a little bit complicated. I think if we would have used the k times k minus 1 times k minus 2 down to k minus n formula, we might have gotten something slightly different than what we have written here, but we still have a series that we'd have the same series nonetheless. It would just be slightly differently represented, but each of these multiples would still be the same. So that's the binomial series in practice. Now, speaking of practice and practical things, well, this might be one of the least practical ways to come up with a power series, but it is just another thing we can do to come up with a series. So we're asked to find the first three non-zero terms in the Maclaurin series for secant of x. Okay, we could try the long way, and that would be, let's start finding the derivatives of secant of x. Remember, that's not very nice. The derivative of secant of x is secant x tangent x, so that would be one line. Then you need the derivative of secant x tangent x. The problem with that is that's going to be a product rule. As soon as we have product rules, we start to make a mess. So we really don't want to go that route. So what we recognize is that the secant of x is 1 over cosine of x. And this is the point where I introduced the fact that we can multiply power series expansions of functions. We can multiply, we could divide them. In this case, what we'll do is we'll divide 1 by cosine of x, and we'll divide 1 by this version of cosine of x. It's just like polynomial division, only there's infinitely many terms. Luckily, we just need to find the first 3 non-zero terms in the Maclaurin series for secant of x. So in other words, just the first 3 terms. So to do that, I'll write it as 1 over this power series representation of cosine x, maybe not so useful, but the next line is 1 over this polynomial, this infinitely long polynomial. Now, just to do the details of that, well, we write 1 inside this division bracket, and we write what we're dividing by out here. This is this term expanded. Remember that 4 factorial is 24, 6 factorial is 720. And what we've done is just carried out polynomial division. Remember, what you need to do is you need to zero out this term, the lead term here, so to speak, or the first term that shows up, with this whatever coefficient makes sense. We'll multiply this expression by 1. We'll multiply this expression by this 1. And we get this line here. We change all the signs. That's been done in red here. And then we add up this and this, and we get rid of the 1, but we add a positive x squared over 2 minus x to the 4th over 24 plus x to the 6th over 720 minus infinitely long stuff right here. We go this far because I just know in advance, or just took a guess, possibly, that we need to go to 4 terms in order to get 3 terms from this division. If you needed more, you could always write those down and add them, or append them to the problem, or redo the division so you have enough terms here to make it happen. So the next thing, this is our sort of lead term here. We need to zero this out by multiplying it against this term right here. Well, I pick x squared over 2 because that times 1 will match this term right below it here, and then we'll change the signs to add everything up. Now, the remaining terms come from this x squared over 2 times negative x squared over 2, which gives us this one, then times this one to get this one, and so on. We could continue it to here, but I realized we didn't actually need that one, so I did not do that. It's nice to have that detail just in case. Anyway, we've got enough written out. We're ready to add change the signs and add these things. And we should see as we do that these two add to 0, and we're left with this new lead term. We add its coefficients, we get 5 over 24x to the 4th. At this point in the division, we've got this term and this term, and we're looking at this term that we need to zero out, and we know that, okay, well, I need to multiply this 1 by exactly this, something that matches this term, so that way I'll get it below it, and I can keep going. But at this point, I've gotten the fact that this term is what it is. I now have the first 3 terms of this division, so I can say that secant of x is approximately 1 plus x squared over 2 plus 5 over 24x to the 4th. And since I've got 3 terms, I've met my requirement and I'm done. If I needed 4 terms, well, then I'd probably have to write out maybe what some of these are, or at least have done the careful work of adding these 2 up, which I guess did happen. We just didn't use it. Maybe we wouldn't need it for 4 terms. We might have enough to get 4 terms by carrying out what's left right here. So a little bit of trial and error and experience on the student's part should totally clarify that. In fact, I think we can get a 4th term with just these, just by looking at it. So that's nice. Okay, so that's a complicated process. We don't want to have to do that all the time, but it's nice to know that you can. And that's just to approximate the power series for a function. Now, approximating the power series for a function could be somewhat useful because you could then use that truncated. This would be the first 3 terms. Sorry, I shouldn't call it the approximated. That is the actual first 3 terms of this power series, of this function's power series. It's just a little bit hard to get to them. It's hard to develop them. And we could use this power series to approximate secant of x if it fit our purposes, our requirements for accuracy and precision. Now, approximating integrals with Taylor series. This is our, again, touching on our use of this thing. And finally, we're at a point where, okay, we're going to look at an indefinite a definite integral. So we're going from 0 to 1, integrating from 0 to 1, the function sine of x to the 4th dx. They're asking us to take it to 4 decimal places. I won't do the full details of the decimal, but I'll get us set up to do so. So we've got the integral of sine of x to the 4th dx. Well, I don't know how to integrate that directly, right? And I'm thinking of it as an indefinite integral first, because maybe I can get a representation through Taylor series or Maclaurin series that'll help us evaluate this definite integral. Well, if u was x to the 4th, then this integral would be the integral of the series sine of u, and sine of u has power series representation this. We did this earlier in these notes. So we write that down, but then we realize that u is x to the 4th, so we can swap that out here, x to the 4th to the 2n plus 1. We still have an integral of this power series, but we know that the integral of a power series is the series of the integrals of the terms, right? So then we just integrate the function of x that's in here. Remember, all this other stuff is not a function of x, so it's not integrated. It's moved outside of that integral sign. X to the 4th to the 2n plus 1. Remember that we'll have to multiply these two exponents together up here to get 8n plus 4, as we see here. The antiderivative of that is x to the 8n plus 5 over 8n plus 5. That's our capital F of x function. That's our antiderivative, our indefinite integral of this function. That's very useful. It's nice to write it this way, and we'll see why just below. If we remember the fundamental theorem of calculus, capital F of 1 minus capital F of 0 is the definite integral. So in other words, this definite integral is written as f of 1 minus f of 0, capital F being the antiderivative. We didn't bother with a constant here, plus c, because we know that we're going to evaluate a definite integral, so we don't need that constant. It would just subtract out anyway if we picked anything other than 0. So we just picked 0 here. So f of 1 minus f of 0, well, this is a power series minus another power series. Many of the problems we see involving these, most of them should allow these two series to either one will cancel out or we can combine them in some useful way, some pairing into a single summation notation. In this case, what's nice, it's f of 1 minus f of 0. Well, we're just plugging in 1 for x and 0 for x in each of these. We plug in 0 for x in this expression, and that's going to zero out every term other than the first term, right? The to the power of 1 term. And even, sorry, that's going to zero out all terms because when n equals 0, x to the 8n plus 5 is going to be x to the 5th still. So when n x will be 0, so it's 0 to the 5th, and everything is zeroed out. So there's no constant term to come out of this whatsoever. So this whole series just zeroes out. And what we're left with is the f of 1 portion of the series. And that has been somewhat simplified. I just put these two denominators together over an alternating series. And what we need to do is approximate this alternating series here to 4 decimal places. And if you remember to approximate an alternating series, we did this a few videos ago, I think in 8.4 in those notes, you just need to write out terms until you get to the desired level of accuracy. So you get to a term that was 0.00001 or less than that, or strictly less than 0.00001, 4 zeros and a 1 to the right of the decimal point. And once you find that term, then you just add up the terms that came before it, because an alternating series is bounded by the first term of its tail. Remember, it's bounded by b sub n plus 1. So definitely have a look back at section 8.4, I believe it is, where we did some of that approximation to be able to complete this approximation to 4 decimal places. So there it is. That's one of our nice uses of the Taylor series or Maclaurin series to evaluate, to handle an integral that is definite integral that we just certainly couldn't do directly by an antiderivative method. Convert to a power series, find the antiderivative, and then apply the limits of integration. So again, the class has almost always been about integrating things, and it still sort of remains about that. It took us a lot of work to get to a point where we could build such a tool and use such a thing, but in the end, our purpose was essentially along these lines. Now, again, that's not the only use for Taylor series and Maclaurin series. There's quite a bit that we can do with those approximations, and it's just all over physics and mathematics in general. So it's a very useful thing. So be sure to practice these and become fluent in them for the future.